Hey guys, tonight I'm going to create a video for you about empirical formulas. Empirical formulas are pretty easy and they're very central to our understandings in chemistry. So hopefully after going through this video tonight you'll have a pretty good understanding of what's going on with them. So let's talk about what an empirical formula is first. Very simply, an empirical formula is the simplest whole number ratio that exists between substances. So for example, if we have a substance such as CH4, okay, we can see that there's a ratio of 1 atom of carbon for every 4 atoms of hydrogen. You can't get any more simple than that 1:4 ratio, so therefore it's an empirical formula. A different example would be C6H12O6, which is for glucose. We can see that there is a 6 to 12 to 6 ratio that we can actually simplify to break down as an empirical formula into being CH2O. So you can see that this 1 to 2 to 1 ratio is more simple. Therefore, that's the empirical formula. C6H12O6 is not the empirical formula. It's actually the molecular formula. Another example could be something like CH, okay? Better yet, C2H2, which is acetylene, okay, or ethine, okay. It's used for welding. It's a gas. We can see obviously that, and here I am, I got this all written funny here, C2H2, which is ethine. It can be broken down into CH. Not only can C2H2 break down into CH, but also C6H6 can be broken down into CH as well. Okay, so the point that I'm trying to make here is that an empirical formula is the simplest whole number ratio between atoms in a substance. You can't get any more simple than CH in these two cases, CH2O in this case, or CH4 in this case, so those are empirical formulas. If you can simplify it a little more, such as these examples right here, you can see that these right here, these three examples right here, are what we would call molecular formulas. Okay, so empirical formulas are the simplest whole number ratios. Molecular formulas are not necessarily the simplest whole number ratios, but rather the ratio of atoms in a molecule. It is very possible for the empirical formula to be the same as the molecular formula, such as in CH4 right here, which is methane. Okay. Natural gas, major component, and natural gas. Can't get any more simple than CH4, and it happens to be the actual molecule. Let's talk about some calculations. Okay, the biggest thing to remember is that what we're looking at here is not only that it's the simplest ratio of substances, but it's the simplest ratio of moles of substances. I'm just going to go ahead and clear this out really quick. Okay, and then we'll go back into our screen right here. Okay, so here we go. Let's go ahead and look at a calculation. For example, get back into here. Okay, so for example, we can have a situation where we have something which is 11.66 grams of iron and 5.01 grams of oxygen. So when we look at this, we can see that there's a mass ratio of mass of iron to mass of oxygen. But what I want you to think about for a second is that the formula is going to have some formula, FeXOY, okay, where there's going to be some number that represents X and some number that represents Y. Here's the key, okay? The key is that if we had 1 mole of FeXOY, there would be X number of moles of Fe, okay, and there would be Y moles of O that make up that formula. So the key is we want to figure out what's that mole ratio, and we talked about that the other day. Okay, so if we want to go ahead and try to figure that out, we should be able to work our way through it relatively easily. Okay, so what we have is we've got masses, okay, we've got masses over here of iron and masses of oxygen. So what we need to do is we need to convert those masses into moles. So how do we go about doing that? Well, very simply, we're going to say, all right, over 1 for every 1 mole of iron, there are some number of grams of iron. We get that by going to the periodic table, which I happen to have up right here. We can see iron's right here. We can see it's 55.845. Remember, we're going to round to 2 decimal places for our molar masses, so we'll call 55.85 grams of iron for every 1 mole. So there's going to be 55.85 grams of iron. Now if we go to our calculator, we can see it's 11.66 divided by 55.85. So we've got 11.66 divided by 55.85, okay, which works out to be 0.209. We should carry it to 4 significant figures because that's what we have here. 0.2088 moles of iron. So let's go ahead and figure that out. Equals 0.2088 moles of iron. Okay, so that's for the iron part, which is pretty straightforward. We do the same for oxygen. Put that over 1 times for every 1 mole of oxygen. Again, we go to the periodic table. You probably have this one memorized right now, but we look at oxygen, 15.999. Come back over here. We can see that it's going to be equal to 16.00 grams of oxygen. By the time we round it to our 2 decimal places, figure out our conversion now, which is going to be 5.01 divided by 16.00, which equals 0.3131. Okay, equals 0.3131 moles of oxygen. Now, so the problem is when we look at this example here, we can see that there aren't whole number ratios here. If we go back to the original idea that our formula is going to be FEXOY, we know that x and y have to be whole numbers. So the question is, how do we turn them into whole numbers? Well, it's pretty straightforward. What we're going to do is we're going to divide everything by the smallest number of moles. In this case, the smallest number of moles are 0.2088 moles of iron. So if we divide everything by the smallest number of moles, what that's going to do is that's going to turn this 0.2088 divided by 0.2088 is going to equal 1. In this case, if we take in this and divide it by 0.2088, okay, go over to our calculator over here, 0.3131 divided by 0.2088 equals almost exactly 1.5, okay, equals, oh, make sure I get back into the right screen here, equals almost exactly 1.5. So what that tells us is that there is a 1 to 1.5 ratio of iron to oxygen. Again, going back to our original idea, FEXOY, that means we have FE1O 1.5. Well, the problem with that is those aren't whole number ratios. So what can we do to turn this into a whole number ratio? It's simple. We divide everything, in this case, by 2. Divide this by 2, divide this by 2. That now turns your FE into 2, FE2, and your O into 3. You can see here Fe2O3 is the simplest whole number ratio that exists between iron and oxygen in this situation. Okay, so let's go through the steps again. We had masses that we started with, we converted them to moles because we wanted to find the mole ratio, the X to Y ratio that was going on in this situation here. Okay, the problem was that we didn't have whole numbers. By dividing by the smallest number of whole numbers, 0.2088 in both cases, that would tell us the smallest ratio. That converts your iron number of moles into 1 mole of iron. The problem is that the oxygen became 1.5 moles. Okay, because 1.5 is not a whole number, multiplying it by 2 turns it into 3. Okay, but if we multiply this by 2, we also have to multiply the iron by 2 as a consequence. A 2 to 3 ratio is the smallest whole number ratio. Okay, pretty straightforward. All right, let's take a look at another example. As another example, we've got, for example, 5.28, whoops, sorry about that, 5.28 grams of tin, okay, and we've got 3.37 grams of fluorine. Okay, so let's take and convert each one into moles first. Divide it by 1. We know that for every 1 mole of tin, you're going to have some number of grams that are associated with it. So we come over here, find the periodic table for tin, 118.71. Okay. Oops. Divided by 118.71. 19.71 grams of tin. Go ahead and perform our calculation. We can see that it's going to be 5.28 divided by 118.71, and that's going to equal approximately 0.0445. Okay, keeping the significant numbers consistent. 0.0445 moles of tin. Now we do the same thing for the fluorine. Divide by 1 times, we know that every 1 mole of fluorine is going to equal some number of grams. In this case, it's 18.998 or 19.00 to keep it consistent, divided by 19.00 grams of fluorine. Okay, perform the calculation. We can see that it's 3.37 divided by 19.00, and that gives us a ratio equal to, not sure why I'm showing up on my Twitter, but that's okay, equals 0.177. Okay, keeping the significant figures consistent, moles of fluorine. Okay, then we're going to go ahead and divide everything by the smallest number of moles, in this case 0.0445 divided by 0.0445. When we do this, we can figure out that it's going to be 1 mole of tin divided by 0.0445, 0.0445, back to our calculator. We can see that it's 0.177 divided by 0.0445, and that's equal to approximately 4. You can see that's really close to 4, equal to 3.97, okay, because it's really close to 4. We'll round it up to 4 moles of fluorine. And now, because that's a consistent ratio of whole numbers, we can see that our formula is going to be SnF4. Now, as an extra step, we could go ahead and name this thing. We know that it's going to be tin. We know that it's going to have some Roman numeral because tin is a transition metal, and we know it's going to be fluoride. Okay, each fluorine has a -1 charge. There are 4 of them, so it's -4. That means your tin must be +4. Tin 4 fluoride. Okay, let's go ahead and take a look at just one last example, and then we'll be all set and good to go. Okay, last example I want to look at would be if we had a situation where we had percents of substances. So let's say we're looking at a substance, and in the substance we've got 87.5%. I'm going to go ahead and use my consistent colors. So it's 87.5% of nitrogen, and it's going to be 12.5% oxygen. Okay, we can assume that these are percents by mass. Now here's what's interesting about this. If we assume that our sample is 100 grams, okay, that's the key. We want to make an assumption that our sample is 100 grams. 87.5% nitrogen actually works out to be 87.5, we'll change the color here, go to green, 87.5 grams of nitrogen. And similarly, 12.5% oxygen is 12.5 grams of oxygen. Again, the key here is that if we assume a 100-gram sample, if we assume that our sample size is 100 grams, it works out. You can assume your sample size is going to be anything. You know 87.5% of it is nitrogen. By saying it's a 100-gram sample, literally all you do is you're changing your percent to grams. Okay, so that's why I recommend that. We'll go ahead and, using the same convention we had before, we'll go ahead and convert those to moles. We know that 1 mole of nitrogen is going to equal some number of grams. How many grams does that equal? Go to nitrogen, 14.01. So it's 1 mole of nitrogen is 14.01 grams of nitrogen. Go ahead and perform that calculation. 87.5 divided by 14.01, and we can see that it's equal to keeping 3 significant figures, 6.25 equals, nope, didn't convert it over the way I wanted it to. There we go. Equals 6.25 moles of nitrogen. Okay, and I'm going to go ahead and erase our assume now. Better yet, no, I'm not going to erase it. I'm going to go ahead and just grab the whole thing here. I'm going to move that down there so we remember. Okay, not down there because I'm going to cover that up. Down here so we remember. Okay, so we've got 6.25 moles of nitrogen. We do the same thing for oxygen over 1 times 1 mole of oxygen. We remember from before it's 16.00 grams of oxygen. Okay, so we can go ahead to our calculator. We can say it's going to be 12.5 divided by 16.00, which equals about 0.781. Okay, about approximately 0.781 moles of oxygen. Clearly, that's the lowest number of moles. We're going to divide everything by that. Divide by 0.0781. This is going to equal 1 mole of oxygen. 6.25 divided by 0.781 is going to equal, don't know, got to get it done, 6.25 divided by 0.781 is approximately 8, almost equal to 8. So we can see that this is, get back into the screen here, is almost exactly 8 moles of nitrogen. In this case now what we know is that we can go ahead and perform this conversion, the conversion's already done. We can see that it's going to be N8O, okay?